But it's so interesting, like black holes in general. Like
Yeah,
you think
I agree.
about a black hole. The size of a black hole is a zero, right? But the reason why we actually see an empty black dot is simply the physical properties of the black hole. That
Mm-hmm.
infinite curvature means that at some point, like those funnels when you like donate money in those things and then the money like
Perfect
goes
example.
around, right? Like there's a point where like photons is like that money that you put in, and it could like if it's far enough away, right? The curvature is not that intense. It'll
Mm.
curve but keep going. There's also at the Schwarzschild radius, the photon sphere,
Mm.
where it'll curve and it'll just orbit. Like the photons will be satellites to the
Basically,
black hole and just
basically.
orbit there, until something happens, I guess.
Mm-hmm.
Um, but if you go past the photon sphere, then like the slope is too slippery for anything, right?
It
As soon
is.
as you pass the photon sphere, you know, there there's oil, you can't
Can't
get out.
leave.
You're
Can't leave.
just you're going on down on ice.
Mm-hmm. And
Your
interestingly
faith
enough,
is
in a black hole, the more you struggle, the faster you go down. Just
mm,
by the way that space is constructed, I mean, even though inevitably you will die, the slowest way to die would be to stay completely still. Now, not that any of us are really
mm,
going in a black hole anytime soon, but it was just an interesting thing that I had read somewhere because the whole idea of a black hole is pretty cool. Because a fundamental thing that it does, and I think we've spoken about this before, and I know we're just kind of getting into black holes here a little bit,
mhm.
but I just wanted to talk about the whole idea of spaghettification because I think it's
Yeah.
really funny.
Wait, before you say that, I just want to say something that's really interesting is that
Okay.
as you're approaching a black hole, right? Like when you cross the Schwarzschild radius, you don't feel anything, right? Because it's empty space, right?
It
So
is.
so as you're approaching a black hole, what you see is like there's a black sphere in front of you, and then the universe is everywhere else where you see like stars and galaxies. As you cross the photon sphere, your field of vision actually becomes 50-50. In front of you, like if you look to the left and you look to the right, it'll be split. Even if you look up or down, in front of you will be completely black and behind you will be universe.
Mm-hmm.
And when you enter the black hole and you turn around, it's like the opposite as when you were outside of the black hole. What happens is that your entire field of vision is black, and when you look behind you, there's this sphere that is the entire universe that is slowly shrinking and shrinking into nothingness as you approach the center of the black hole. So there's kind of this awesome like uh, like I want to compare this to like particle and antiparticle, right? Like when
Mm-hmm.
you're outside of the black hole, there's universe, black hole,
Mm-hmm.
and when you're inside of the black hole, there's black hole, universe.
Mm-hmm. And the
Yeah.
coolest thing about all this is that even though the light is so wonky, it's still traveling in straight lines with respect to itself, because it's just that space is so wonky in a black hole and it's so curved that technically, by the definition of straight line, it is traveling in a straight line. It's just that the line itself has now been curved, which is really interesting. You know how you can make that classic line a circle. So it's basically that whole thing all over, and it's so cool because I think I was listening to this one. Wasn't it in a black hole where like you can see you can for the first you can like see the
Yeah.
back of your head or something like that?
When you're on the photon sphere.
You can see the back of
And
your head, right? Yeah, that's
yeah,
pretty
because
cool.
the photons are orbiting, so it goes like around and
So cool,
into
man.
your eyes.
Light's so
But
messed
one
up.
thing that's super interesting is time dilation. When you're in a strong gravitational field,
Yeah,
your time slows down.
it does.
If let's say Rayhan, you go into a black hole,
Oh no.
according to me here on Earth, you would be immortalized, because in my perspective, your time has dilated to infinity, and so you would just like I would be long gone before, and you would just still be chilling in the black hole.
So that's why the interesting thing about it is no, but also another interesting thing about if you're like looking at someone move into a black hole, you'll just see them there basically stagnant
Yeah.
until they die because until they basically just.
Yeah.
But
Well,
like
once
because
they,
of how
once they actually cross the Schwarzschild radius, you wouldn't be able to see like any update, right?
yeah, any
Because-
update, but you'll still see
yeah.
that same image because the light
before it
before
it
exactly
crosses,
before it went in, right? And that's the whole cool concept behind this, like the whole notion of this whole thing is pretty fundamental, and it's nice. It's cool.
Yeah.
For sure.
So to those listening right now, I hope you enjoyed this discussion on gravitational waves, the force of gravity / space-time curvature, and black holes.
What was I just gonna say? I was literally just gonna say something before I botched that whole thing up.
Oh yeah, no, you're right. You were gonna say something and I interrupted you. And
No, I was talking about spaghettification. Screw that. No, that had nothing to do with this.
That's right,
But I wanted to
right.
talk about. Oh yeah, time dilation. A cool thing about that. Did you know if you stand near the pyramids, your time is moving slower than mine?
Wow.
Yeah. Just so the pyramids, right? I mean, I say the pyramids because it's a very massive object, but anything really very massive, if technically you're standing near it, believe it or not, obviously to fractions of seconds that you can't even perceive, but your time is actually traveling, or your time is being dilated. So it is being stretched, so you're basically traveling in a slower field because not of a gravitational field or anything like that. No force, simply because of mass. Because of how mass curves space. And how when you're in that space, your time is now also dependent on that curved space. And that original discussion about how, just how time is bending, and bent time versus bent space, and understanding that relationship is pretty cool.